welcome back to Advent of Code 2019. Day 18. We're on to part 2. So, last time we had this map. With a bunch of keys and doors, and we had to find the shortest route in which we can pick up all the keys, noting that you can only get past a door if you're holding a certain key. Okay, that was the problem. And then part 2 was the same map, but we change. So this is the starting point. We change that to look like this, so that you've got 4 separate starting points. And yeah, and you got to basically do it again, but you've got 4 parallel robots. Not parallel. Well, they are. I don't know. They're independent of each other, but you kind of need to get a key for other. If you pick up, say, if one robot picks up key A, then the other robot is able to go through door A. So they all have the key essentially. So. Hello, DJ. So I'm thinking if you pick up a key to a door, then logically the very next step should be to go to that door, whether you go to that door or one of the other robots goes to the door. Because otherwise, why would you pick up the key? Oh, no, that's not true. The answer to why would you pick up the key is because it's nearby, and later on it won't be within reach. Okay, forget that line of reasoning. So I would think this is really same as before. Not breadth first search, Dijkstra. But it's trickier. Let's stop the music as well. Because our state space is the 4 different locations the robots are in. And as coupled with the amount of keys we're holding across all 4 robots. So does that make it much harder than part 1? It kind of breaks up the map a bit, but it does also. I don't know. I mean, so one thing we need to. So before I said we would use something like Floyd-Warshall's algorithm to work out all the paths. That was wrong. Well, not quite. In a tree, you don't need to use Floyd-Warshall's algorithm. You just run breadth first search from every node, like from every key, to find the distance to every other key. That's quadratic time, isn't it? in the number of keys. No, number of keys times number of spaces. So yeah, that's kind of quadratic time in the number of spaces, but actually less than that. So we don't need to do shortest path algorithm. That's more for things with cycles or negative edges and stuff like that. It works in all cases. Here we've got a tree, so it's just far simpler. So we can work out, pre-compute the distance between every pair of keys and the set of doors that are along that route. So you can only go that route if you have all those doors, all those keys for those doors. Okay. So that's what we need to. So let's rewrite BFS, and I'm guessing once we do that, we run part 1 again. It should be much quicker because we just use those values. Let me grab a drink. So let's do that then. So we want to first rewrite BFS. Well, not BFS. BFS is... well... get reachable keys. Yeah, get reachable keys from a spot is going to... hang on. there is a slight issue here, because if there are 2 keys along a route, we don't really want the further key to be a node that's reachable, because or do we? Because we might collect the intermediate key and then... Oh man, this is a bit confusing actually. Because what are we actually trying to do with this BFS? What is the end goal? We want this. Is this the same puzzle from a couple of days ago? Yes, part 2. I didn't try part 2 before, only part 1. I reckon it doesn't matter. I think we just find the distances between every pair of keys, regardless if the route includes another key. Because even if we take a suboptimal route where we walk over a key, we can pretend we just ignore it, just leave it on the floor. Now, you're not allowed to do that, but it's not harming us by pretending we're leaving it on the floor, because there'll always be a shorter route where we did stop at that key and pick it up, and we'll probably find that using the algorithm. So it doesn't matter if we allow ourselves to ignore keys. It doesn't make it worse. So yeah, this method is going to find... Let's make some notes here. Find distance and doors and accumulated doors in all key to key parts. Doors. Okay. Okay. So our state is going to be just like well, held keys doesn't matter now. Okay, take that out. Just finding all reachable keys from start, and for each key, should we say, for each key pair in the hash table, we have a pair. The result will be a pair with the door, the distance, and the doors. Something like that. So, and then no. The index of the table will be the one key, and as a result will be a triplet. Oh no, wait, no. Wait, how do we do this? Okay, the index of this table will be... Oh, no, we're starting at a specific location. So we actually just want a list of locations along with their distances and door paths. Is that it? Yeah, something like that. So we get list of key destinations. Okay, fine. Let's get started on this. So Q, use a DQ, but start. So the state is not going to be just the location. But oh yeah, it could just be the location. But we'll need another map. Doors. Okay. That's... oh, it's not as... it's going to be an empty set. So that is a mapping of locations to how many doors you would have passed if you reached that location. What? No, not how many. The full set of all doors you will pass on the way to that location. So we start off with empty set, 0 distance, put it in the queue. Alright. So we fetch... so if we arrive at a key... and... so if it's a key... we don't need this anymore. Then... keys... so just say result is this. So we're going to do result.append. So the result we want is the distance. So it'll be no. The actual key. So it'd be the letter. So that distance. The letter, the distance, and the set of doors. So, doors. And then... but we don't continue. Carry on, because we still need to expand more nodes from here. Ooh. Okay. If required key... oh yeah, we're not doing this. Okay. So for each neighbor, you get neighbor's current. If it's in dist, that means we've done it before, so skip it. So the dist of the new neighbor is +1, correct. If the new neighbor is a door. So if... What's the method we have here? Required key. If self.required key of instead of saying doors, let's say required keys. Because we don't care about the capital ones, we care about the lowercase ones. So required keys. So if self.required key of neighbor is not none, that means it's a door, then new then required keys of this neighbor is gonna be required keys of current union with this particular key. Else it will just be this alone. Number of the doors keys required for this path is the same as keys required for the previous node. And then q.append neighbor. Is that first one supposed to be key or keys? This variable here? This variable is a set of keys. And right above it, this one. This is a unique. This is one key or none. It's one or none. It's telling us what is the key that's required to enter this specific spot on the map. So it's either an empty spot, in which case it's none. It should return none, or it's just one letter. So the keys set will add in that one letter as a singleton. If it's not none, and if it is none, then we just copy the required keys set for the previous node into the new node. So this should just accumulate keys, and because it's a tree, there's a unique path between locations. So we never deal with multiple paths with different key sets to a goal. Hopefully. It looks like it's a tree. I'm trusting it to be a tree. Let me put that on the queue. Then we return result. So we search the whole map. So if we just run this for every key, we should just get a list of reachable keys. Alright, we'll try. And then this needs to be reworked. So just comment this out for now. So does this run? Okay, now we need to actually populate this. So we say key, or I don't know, path table equals that. Alright, so we want to try every key location as well as the starting location. So we want to say for start in, so it's going to be so it'll be grid dot start alright, this is grid.start will actually have to be a list because there can be multiple starts. So let's say it starts off in this empty list. Starts. Self.starts dot append that. Okay, so for each possible start, and initially that'll just be one thing. So it'll be grid.starts, that's a list on its own, plus all the keys, grid.keys, that should also be a list. Yeah, oh, it's a hash map. Because we're mapping... what are we mapping? We're mapping characters to positions. Alright, so we want... Basically we want grid.keys.values to get the positions. Should be fine. We do grid.get reachable keys from this particular start. I'm going to try running that now, see what happens. Can only concatenate list, oh for goodness sake. List, cast it to a list. Okay, so it just ran BFS from every start location. Now we want to get destinations equals that, so that's going to be a list, or just say for. So it's going to be 3 things. It will be the position, the distance, and the set of keys you need. So for position, distance, required keys in that. Path table. So this variable here maps what? Right, let's say path table start is an empty list to begin with, and we just pile things into it. path table start dot append this triplet. Is that what we want? Position, the distance, and the required keys. Position, pos. We'll just say for triplet. Just put the triplet in as a tuple. Wait, what am I doing here? Just say path table start equals this. Yeah, that's it. It just goes. We just take the output of that and put it into the map. So is that fine so far? Okay. Try printing path table now. It's going to be a bit bulky. So position I40J40 maps to a list. So it's saying H so that get pos. What does get pos do? Oh, get doesn't get the position. We don't want that. We want literally just the vector current. Okay, so I4040 map. All the reachable keys are this one. So it's whatever's there. Wait, are we skipping? If self.isKey current, if we start from a key, we don't actually want to add it to this list. So if current not equal to start and okay. Oh, no. Like that. Yeah, we don't want to add the start to its own list. Okay. Try that. So, for example, 4040. Is that the start location? I think so. With possible reachable places are this one at distance 10. No doors are required. And there are some 2969. It's distance 420 and has all these doors on the way. So some of these need a lot of doors. Okay, it looks about right. I mean, I could test an example to make sure these are actually correct, but the variance here looks roughly what I would expect, so... And this far away one needs all these doors. Okay. Okay. So now, we have this path table which is fixed. We never have to recompute it. So now if we run Dijkstra using this path table, we never have to compute any more intermediate distances. It's all stored here. So we want to run Dijkstra from a starting location to a goal. What's goal again? Number of keys. Okay. Let's rename that to goal num keys. Okay. And we want to give the path table as well. Given start a number of keys we're aiming for, and we want to find the shortest route to get to that goal number of keys, which is all keys basically, and given a path table. All right. We don't need this anymore. X keys. So given a state, which is a position, and a set of held keys. Yeah, let's do that. So we start off with start set 0, blah blah blah. So this all stays the same. We're not doing this. If we get to the goal number of keys, we return the distance. Yep, sure. All right. Reachable keys. This is the bit where we're doing a massive amount of computation. So instead of doing this, take that out. So we're computing all the neighbors. We're going to want to go for each. So for it's going to be so basically neighbor, path, distance, required keys in path table for the key that we're sitting on, the location we're sitting on, which is current pos, neighbor, so neighbor state, so neighbor pos, okay, call it neighbor. Neighbor is a state. Neighbor is going to be get state of neighbor pos and union with key. Why did I do it like this? Oh, I see. Yeah, okay. So the key will actually be grid.get pos neighbor pos. That gets the key. So current held keys, we add one new key to our current held keys, our keyring, essentially. Neighbor distance equals that path distance, which we pre-computed, added. So for these required keys, what are we doing about that? We're saying we're only counting this neighbor if required keys is fully contained within the set of keys we're holding. But what if you were to get a key along that path that you would use? Well, we're not really counting that, are we? So we'll say that path is invalid, and we'd actually have to go to the intermediate key first. Makes sense. All right. So we say if what is this the method we use here? Python set containment. We want to say if is a subset of another one. T dot is subset of S. So we want to say if required keys dot is, what is the method? Is subset of current held keys. So if these keys will let me cover all those doors, or if it's not a subset, then we can't pass those doors, so we skip this neighbor. So only the ones which we haven't seen before will end up added to the queue. Alright, will that work? Don't print this. So we want just that. Length grids, keys. So the goal is that many keys. We need to provide the path table. Alright, try it now. How long is it going to take? Quicker than before. Much quicker than before. Still longer than I was expecting. Well, seems about right, maybe. And we can print this just to see the progress being made. Yeah, it slows down a bit, but way faster than what we had before. 3216, is that the correct answer? 3216. Correct for part 1. Alright. So we've redone part 1 in a much more efficient way. A bit more confusing to understand now, but that's sped it up from minutes to seconds. Alright, good. Now, part 2. So do we want to make Dijkstra a general case, or we'll make a duplicate of Dijkstra and modify it slightly? Let's do the latter. So we're gonna say okay. Part 1. Just put part 1 here. So now part 2. Will be... Alright, we no longer need to print that. Or... this. Alright, and then... defining a new Dijkstra. Subtly different. Dijkstra 2. Given 4 starting locations. So it's going to be a tuple of specifically 4 starting locations. Go num keys is the same. Path table is the same. Now, path table will actually be simpler this time, because we've broken up the map, so the reachable keys from each key is is less. The number of... Yeah, because there'll be fewer keys reachable each time because we can't cross the middle. We could put those on. Alright, so we're given 4 starts. Or a tuple of starts, I guess. Just say 4 because we know it's 4. So you got get state of, let's just call it pos tuple so we don't forget it's a tuple. It's that initial state equals get state of starts set. Initial state distance is 0. Okay, this is going to be as normal. Tuple. String equals current held keys equals that. If length current held keys equals goal num keys, return distance. Okay, that's as before. Oh yeah, we could do that as well. All right, now this bit changes. So this time we're going for each pos in this 4-length tuple. We're trying to find the path from that particular key position. So how are we doing this? We're going to say for I in range, or say for, let's say, pos tuple index pos in enumerate current pos tuple. So we go 0, 1, 2, 3. And then for that whole thing, so we've chosen one index to fix, and we're saying for this index, we're going to go from this particular pos to the next key available. So it's going to be for neighbor pos, path distance required keys in path table, it's gonna be that, I guess. And then this is what will stay the same. Now this is gonna be different. We're gonna say, so neighbor. Yeah, it's not quite going to be that. So yeah, if we don't have the keys, we don't take this part. Otherwise, we do. All right, so we're saying this particular position in the tuple is going to change to whatever we get here. But everything else will stay the same. So it's going to be like new pos tuple equals list of current pos tuples. So turn it into a list. Change this particular index to the new position. And then tuple it up again. Just a long-winded way of doing that. Alright. And then, once we have that, the neighbor, the overall neighbor is going to be getState using this tuple. Those keys. And the key that's picked up at that specific one spot. Neighbor distance equals distance of current. What was current? Yeah, current is that. Why doesn't it like this? We've done dist current here, but it doesn't like us doing dist current here. What exactly is current again? What's this? Should be fine. Or it doesn't like this statement here? I don't know. So the new distance will be previous distance plus the path distance, which we get from here. If neighbor is in dist, and we found shorter path before, continue. Update that, and then put that in there. Should work then. So we're moving all the 4 robots turn by turn. So in each step, in each phase, we take one robot of the 4, send him to one of the keys he can reach, add up the total distance he took to get there, but also make sure that all the doors along that path we currently have the keys for. And then that's a new state, right? And then just do that. So now that is the new Dijkstra. We have to change the modify the grid. We're gonna have to say we're gonna have to make the grid mutable. So say grid equals, it's going to be list row or row in grid dot grid. Convert everything to a list. So just check that looks correct. We don't need to do part 1 anymore, just turn that off. So yeah, now it's mutable. Okay. So center equals grid.starts 0. Print center. Because that should be okay, 40/40. So now we're gonna have to change each of these things according to what they said. So How does it work? So grid dot grid. So the row will be, I don't know, just hang on. Center is a pos. Alright, so center dot I center dot j equals, oh, hang on. So this one is going to be, okay, start from the row above. So it's going to be row -1, and then start from the leftmost corner. So that would be j-1. That's going to become an ampersand. And then the next one along so it'll be I-1j will become a hash. And then I-1j plus 1 will become ampersand. And then the middle row, it'll be hash, hash, hash. So it'll be I, and then those J's will be hash, hash. And then the final one will be +1, +1, +1, and it's going to be ampersand, hash, ampersand, like that. Okay. And now should we just make it immutable again? Just nice safety thing. So now grid.grid equals dot join row for row in grid.grid. And now for row in grid.grid print row. Alright, see what this looks like now. So where's the center? There. Alright. Looks alright, I guess. Okay. We don't need that. So now, don't need that. Grid.starts is going to change. So grid.starts equals, so it's now going to be so be center plus, so it'll be -1, -1. And then just, it's going to be the 4 corners. So it'll be center plus pos 1, 1. Center plus, so it'll be 1, -1. Center plus, let's do them in order from left to right. So that'll be -1, 1, -1, -1, -1, 1, 1, -1, 1, 1. Okay. So now the grid is just looking at a new grid. So we can run get reachable keys again, and it should just use the same logic. So do this. Path table is empty. The start in grid.starts plus all the keys. So it's starting from each of the starts as well. Yeah, we add the path table. Make sure that runs. Okay. And now it's the big step. We do this basically. Print Dijkstra2 for it starts. In that path table. Unhashable type list. Initial state. So that should be a tuple. Did we wrap it up as a tuple again? Oh, yeah, of course. Part 2 should be tuple of grid.starts. Not a list. Alright, go. Oh, it's going quite quickly. Okay, it'll take longer than before, but that with that momentum, I think we'll actually get there. The fact that it's taking longer is actually promising, because that means it's doing something different to before. We don't want it just running the same logic as before, because then that'll be wrong. Yeah, it looks like we'll get it. Will it be correct? I don't know. Is that logic correct? Each node... So state space... Seems correct in my head. This will no longer work on part 1 though. We can adjust Dijkstra1. We can reuse Dijkstra2. We just have to pass this starts as a tuple. We'll see if it works. Wow. There we go. 1538. Now, does this sound right? It's half as many, roughly half as many as it was for part 1. Because we've got 4 robots and the space is separated. That sounds right, because then across the robots they're working in conjunction with each other. It should theoretically be quicker, right? To collect all keys. Because you're collecting keys within the 4 segments. Yeah, it should by definition be quicker. You never have to have your robot go across the middle to get somewhere, because he can just send the robot that's already down there. So... yeah. But, is it the correct number? Whew. Correct. Wow. I anticipated running into more trouble here. I felt like the branching complexity might be a bit higher, but it's not much higher. It did take longer to run, so clearly it is higher. But it's balanced by the fact that you've now isolated 4 regions of the map. And you've compartmentalized it. With exception, because you do still need to coordinate. Like, you know, one robot picks up one key that another robot needs. So you're not solving 4 separate problems, each of a quarter of the size. No, you're still solving that one big problem and coordinating the 4 robots together. But branching, there's just not as many branches, because there's either you send one robot to these keys, or you send another robot to these keys, and so on. Before, it was you send this one robot to any of the keys. Every step. So it's just an interesting change. And if we look at the code, I could make this work on part 1 as well. So if we just say this is the new Dijkstra, alright. So we use it, calling that Dijkstra. Get rid of the old Dijkstra. Alright, just move this. To here. Alright, so this is part 1. So starts, yes, that still makes sense. So when we call Dijkstra here, it just says one item, so we want tuple, just like we've done below, convert that to tuple. This is a 1 length tuple, which is fine, you can do that. And then the algorithm should just work. And give us the same answers before. So this is part 1 now. And then it'll move on to part 2. It's a bit quicker. 3216. That is correct. Okay. So this actually is the new and improved general case Dijkstra for an arbitrary number of robots all working in parallel. And starting at different starting positions. In this case, I mean, in part 1 there's just 1. And that's cool. That was a cool problem. It was not actually as hard as I thought it would be. I thought we'd have to be a bit more clever than just running Dijkstra. But Dijkstra is not exactly an easy algorithm. Like, you know, I've done it so many times, and no matter how many times I do it, it's always, you always have to think hard when you're writing it. It never gets easier. Because you always have to customize some part of Dijkstra, so you can't just copy and paste the pseudocode. There's always some twist. There's always something in the, I don't know, like the state space or the distance function, the get neighbors method. Something is always different and different from the norm. You could be, I don't know, like on a hexagonal map, or you could have a scenario where your neighbors, you're only allowed to move in one direction or turn, because we had that this year, didn't we? So your neighbors aren't just, you know, forward, left, right, up, down. Your neighbors are either you move forward or you turn on the spot, and now your new neighbor is still staying in the same place, but you're now facing a different direction. That is one step. So that is a distance. So that's like, that is your neighbor space. Sometimes you have weird measures of distances. Sometimes it's a cyclic map. Sometimes it's acyclic, which was the case here, with exception. There was one cycle at the start, but if you pretend that cycle doesn't exist, because it doesn't matter, that particular cycle didn't matter. Any other cycle probably would, because it would mean there are routes to keys without crossing doors. That would be a whole different problem. I guess that would be NP hard, because that is actually essentially the traveling salesman problem. but in a way it's harder than the traveling salesman problem. Because if you took away all the doors, and it was just a question of getting all the keys, that is still the traveling salesman problem. That is still a hard problem. Shortest path to cover all keys. That's MP hard. Put the doors in, and then suddenly you have something that's even harder. Is it still MP complete? Yes. Because you just give the route and then you have your certificate. So it's still an MP complete problem. But we're on a tree, so that's the key here. Alright, and I quite liked using DQ. I guess I should use DQ more often because it's the syntax is more like a list, and often I interchange using a list or a queue depending on whether it's DFS or BFS. I mean, if right now I were to do this, now it's doing DFS. Oh, okay. You would have to do q.pop, not pop left. But oh, if you do okay, so if we were to forget using DQ, double-ended Q, and use a list, which is the slow way, because now you have to realign the list in memory every time. Let's see how much slower it is out of interest. Pop. So we do pop 0, popping from the front of the list. So now we're not even using a... It's the same speed. Because Python's pretty optimized for small lists. So you're only moving like 20 things in memory, so... No, you're not moving 20 things in memory, you're moving... I guess the depth is... Oh no, this one is... Yeah, this one you only have 20 things in memory. Yeah. So it's not that much slower, but it's good practice to use a queue because it is actually better. I mean, especially if you're doing pathfinding in like a video game or something. At some point, you might be okay with lists, but you would be able to get some better pathfinding, especially if you've got lots of enemies with long distances and stuff, and obstacles for them to get around. Q would probably be better. But you'd be using A star or something, so you'd be using a priority queue. Alright, that was pretty nice problem. Not as hard as I thought it'd be. Let's take a peek at the stats and get a preview of the next day. So it's day 18. So people solved it in... This is both stars. 2 hours. Wow. Really? "45 minutes for 17. For day 18, the one I did, it took them 2 hours. For part 1, up to 50 minutes. That surprises me. Because I wrote Dijkstra and BFS from scratch. But, I mean, I could just have copied in the template that I've written before. and just change the, I don't know, the get neighbors and the states or whatever as needed, it shouldn't take that long. Alright, how long did I take to do that whole thing? This session took me an hour with a bit of waffle. What did the previous session take me? I've got the saved video somewhere here. 18 part 1. 2 hours. So together 3 hours. It took me 3 hours, but that's with a lot of talking and being pretty slow and writing Dijkstra and BFS from scratch instead of, like, people who do this competitively, they'll just have a library stored somewhere where they've done this before, so it's just paste in BFS. Why did it take them 2 hours? I don't understand. Like, it took me... I didn't think I was going particularly fast. It took me 3 hours, and I'm pretty sure if I could knock off an hour if I was doing this, you know, not streaming it. Got my templates of BFS and Dijkstra ready and everything. I would be in the top 100 for sure. But why? Because I didn't think... I'm not exactly competitive at these. I don't know. Maybe that year not many people were competing, or just... I don't know. Strange. Because other years, you know, they've done it really quickly, and I don't think I would beat them. And part 2 was not actually that much harder. It just changed from a 1 start to a 4 start 2 pull. I don't know. I think I would have... This is one particular problem I guess I would have been in the top 100 for then. Alright. It looks like 19 might be a bit easier. And then the rest are all kind of similar in difficulty, but varying numbers of... Well, look, these numbers are very different, but the star graphic, I guess it's all squashed up, so it doesn't... you can't... They're trying to align it with these big ones, so these big ones make the result, have the result of making all these ones all have the same number of stars, when in reality you've got 2842 here and you've got 164 here. That's a big difference in ratios. That's like 10 times, more than 10 times more. But these graphics are the same, but I guess that's just, you can't do much about that. Okay. Oh, and the leaderboard. Catching up. I'm now equal to Pararonia. Pararonia didn't do 18, it seems. Okay, and Captain Coda. I don't think Captain Coda is interested in doing these previous years. He's very busy with other stuff. All right. Cool. So that's 18. So 19 might be a bit easier. I might do it tomorrow. So yeah, nothing else to say. See you next time. At this rate, we might actually get all archived years done before Christmas. Man, that'd be crazy. Alright, bye-bye.